Okay.
It's running, so just
Okay, perfect. Okay, so yeah, thanks for all the work you do in this type of cost action to bring people together from different backgrounds. And so I have a kind of a somewhat remote contribution to this, but hopefully at some point it will become important, and that will be clear, I hope, at the end of my talk. And in this context, I have been interacting with Dennis, and that's why I think this would be nice to have a growing community to know what's going on the instrumentation side, and to see if this can have some potential impact or interest of people from your community. Okay, so it's about intensity correlation, about imaging and quantum optics astrophysics. So I can immediately say that my heart belongs to the quantum optics part of this talk. But to be realistic and to make it practical, I need access to big facilities, in telescopes, and most of the astrophysics colleagues are more interested in the imaging part. So early on in this project, like more than 10 years ago, I had to do some compromise, to mix the imaging and quantum optics part in this project. And so I will give a review what the major part of the community is doing. It's the imaging part. And then I will show why this can be immediately applied and used for quantum optics. And that's where I think most of this cost action community can maybe enter. Okay, so, but first I start with presenting the team. So we are now a growing group of people. So we have people from Institut de Physique in Nice. So that's 4 permanent people here. So William Guérin, Mathilde Lucbar, and Guillaume Labéry, and myself. So we are all permanent people, and we have expertise in cold atom physics. That's how we started, and we still, every one of us runs a cold atom experiment. And then we have 2 PhD students, Sarah and Ilian here, and Romeo joined us for an internship this year. And we have more people coming in fall, 2 more postdocs joining us in fall. And so for this project here for astrophysics, we teamed up with people at the Observatoire de Côte d'Azur. And one of the early adopters of this project was Farrokh Vakili, who was the director of the Observatoire Côte d'Azur initially, and then he joined our research project. And 2 very important members of this collaboration is Jean-Pierre Rivet, who is really in charge of all the facilities on the telescopes. He knows how to run things in daily life. So if you want to make observation, he knows how to do things. And Olivier Lay joined us a little bit later, and he's now the key person to give us access to Mauna Kea. You see here a picture of what happened this morning. So a few hours ago, I just took a short screen cut. Not exactly where we were. It's not the same mountaintop in Hawaii, but it's nearby. And so we have on top of this local team here in Nice. So there's also Clément Courde and Julien Charbet, who are working at the Lunar Ranging Station here in Caerleon, and they are expert in everything which concerns time and frequency, which is very important because we want to go for picosecond time resolution, and this is very important. And so we have now starting international collaboration. So early on, we had the interactions with people in Paranal at the VLT site with Nicolas Schuller and Pierre Bourget. I already mentioned Dennis and Christian Pfeiffer on the project I will mention at the end of this talk. We have collaborations with people in Brazil and Chile about random lasing, which is also on the quantum optic part. And more recently, we now have interactions with people from JPL, NASA, and I will go in more detail about this collaboration, because that's really, I think, important for this quantum optic part at short term. Other things are more long-term projects, but this is really ongoing research, and maybe we get information in the next year. So it's really ongoing. And then we have a whole team of people on CAC, Subaru, Gemini, CFH, and EFR institutes in Hawaii. This list of people is too long, but they are, of course, instrumental if you want to go there to do some observations. Okay, so it's a growing community, and basically I'm usually the salesperson. I'm the ones who sells the carpets, but the work is really done by all the other people. The hard work and the precise work is really done by other people. All of those people here mainly work on the imaging part, and I'm more concerned about the quantum optic part. So I really carry the quantum optics aspect of this. Okay, so here a short outline of the talk, a short introduction about imaging, and what intensity correlation came up in the 80s, which is not only in astrophysics, and why now there's a renewal of this intensity correlation approach for astrophysics. In particular, I will highlight what we did here in Nice. I will give a very brief state of the art from last year, and then I will come to the project which we want to develop in Hawaii and at JPL and in Chile about imaging and quantum optics. Okay, so astrophysical imaging. So the first thing you might know, if you take large telescopes, you get better, more light and better resolution. So this is what Galileo did, and basically he did like black and white pictures and get a lot of information about how things moved around in the universe or in the solar system. And later on in the last century, we added to this black and white intensity information, we added colors, spectra. And this gives us a full new range of information we can gather from what's going on in the universe. And of course, now we send instruments to space, and we have we have a lot of instruments available nowadays, and we can study black holes, dark matter, universe expansion. And so my take on this is that on top of the intensities we see from what's coming from light from space and spectra, colors, we also have gravitational waves, which gives us new information. We have neutrinos. But now I want to add a new eye on the universe, which is quantum optics. And I'm convinced that if we see information which cannot be explained by classical optics from the light we come, we get new insight in what happens in the universe. So this is why I want to develop a quantum optics eye on space. And the examples I give at the end of the talk are hopefully just the first application of quantum optics in astrophysics. Okay, so obviously, so here, the larger the telescope, the better, but sometimes it's difficult to build larger area telescopes. It's very expensive, it's heavy, you cannot send to space. So what has been proposed early on by Michelson is instead of having a single dish to collect the light, he added two mirrors a little bit further away to make an effective aperture, which is larger than the optical collector you have. And then you can get fringes from this to distance, and you get the same angular resolution as if you would have a larger telescope. You get not as much light, but the angular resolution is as if you would have a large telescope. And this has been pushed to the extreme by someone here in Nice, Antoine Labeyrie, in Calais, actually. So he developed two movable telescopes, and he combined the light from a star interfering via the two telescopes on a recommendation desk here. So that's very delicate because you need to make fringes at a few tens or hundreds of meter distance and make it stable at the micron level. So that's a very delicate experiment. But he succeeded in doing this in the 70s, and this is now the technique which is used in Paranal, in Chara. This is the best angular resolution we have so far to look at the universe. And this is now called the VLTI or Chara or Anpoy, with a baseline of a few hundred meters. So it's the same angular resolution as if you would have a telescope of a few hundred meters of diameter, which is nowhere close to what we ever want to build so far. But this is the best we have today. Okay, that's the state of the art of high angular resolution imaging. Now, there has been another way how to do this, so this is what I call the interferometric recombination. So you take light of two telescopes, you recombine it, make fringes, and look at the fringes spacing, and that's how you get the angular diameter of your star. There was another technique which was proposed by Hanbury Brown and Twiss, actually earlier than what Antoine Labeyrie did, and this was by looking at looking at light of two telescopes, but not by recombining and making fringes, but just look at if the photons arrive at the same time at the two telescopes. So look at correlations between the light intensity at the two telescopes. And so this is how it works, just a little bit kind of a more technical slide here. So if you have a starlight or a random emitting surface, this gives you random phased Gaussian amplitudes of the field, and this gives you an intensity diffusion which is exponentially decreasing in intensity. And so this is called the Rayleigh law for spectral statistics. So the P of I is e to the minus I, and once you know this intensity distribution, you can compute all moments. So you can compute the second moment, so it's twice the average intensity squared. You can compute the variance and so on. And so this factor of 2 here is important. So, but it follows from this exponential function here. So, for instance, now if you take in this frozen, for instance, for now speckle field, two detectors which are close together, A and B. Of course, A and B, they see the same intensity, so they will move together. So if you compute the correlation between intensity A and B, it's the same. So it's A squared, and so it's twice the average intensity over all positions. The factor of 2 here. However, if I take two detectors A and C, which are far away, then they are no longer correlated. So the product of AI times AC is the average intensity of AI times average intensity of AC. So it's I squared. So if I take the ratio of these two intensity correlation, I get twice more photon correlation at the same position as distant positions. So this is the kind of photon bunching. Photons want to come together at the same position compared to different positions, different interpretation of this photon bunching effect. But it's classical physics. And so the same holds, so this is now a speckle in space, but the same holds in time. So there's a kind of a coherence, coherence length in space and a coherence time in frequency if you filter the light. And from this, you get how well you can make the photons arrive together at the two telescopes. Okay, so this is photon bunching, a very old feature. And this has been really developed and pushed forward by Hanbury Brown with his colleague Twiss, Richard Twiss, in the 50s. First, they had some ideas, they did some lab experiments, and then they went on to measure intensity correlation from a series A, the brightest time we have, and they could show that by taking two very bad collectors, they could show that they could get an intensity correlation, which decreases as you move the two detectors further away in this spectral grain field. And from this feature here, how fast this decorrelates, you get information about the angular diameter of the star. And so they did this, and this was a big success because they could do angular resolution much better than anything which was possible at that time. So this was a big breakthrough. There was some controversy. People say, no, this has to be wrong. People try to do experiments and they didn't see the same results. So they say, it's wrong. People even say that it's in conflict with quantum mechanics. How can you make interference between two sources? How can photons interfere with two different photons cannot interfere? Only a single photon can interfere. There were a lot of debate in the 50s. And so everything was basically solved by Roy Glauber. So all this debate motivated Roy Glauber to do his quantum theory of photon detection, which was the cornerstone of all the quantum optics we have nowadays. And so this was really the motivation for him to do it, and that's why he got the Nobel Prize a few years ago. And so now we have a very solid theoretical ground how to compute things. So this now is well established. People saw that the experimental effects, there were defects in the experiment which didn't show this bunching, so everything is fine. And so with this support, Hanbury Brown and Twiss, they moved to Australia. They were able to build a whole observatory in Narrabri, and they measured angular diameters of 32 bright stars, better than anything which was possible by other techniques in those days. So that was a big success. It motivated fundamental physics by Roy Glauber, for instance. It pushed forward astrophysics imaging. So wow, this was like a really important thing. But then everything stopped. So why did it stop? It stopped because Hanbury Brown came to Nice and he visited Antoine Laberie in Calais. And in the early 70s, that's when Antoine Laberie saw the fringes. And when he moved, so Hanbury Brown saw the fringes, and he saw the fringes. You can see it in real time. It's a few milliseconds. You see the fringes. And Hanbury Brown, maybe I had this, I didn't have the numbers here, but to get the same information, he needed to integrate over days, many, many hours and days. And so he basically said, okay, this technique of amplitude interferometry had such a much better signal-to-noise ratio in terms of observation time that my technique is just not competing any longer. So everything was stopped. So no one continued. This was the end of the story of intensity correlation when Hanbury Brown visited Antoine Laberie. So, okay, so this was the end of the story. And so now I try to convince you that maybe we have good reasons to come back to this nowadays. And everything at the end of the day is in this formula of signal-to-noise ratio. Why, how does it scale? And why do you think we can do something which might be competing with other techniques which exist today? So first, before we coming back to astrophysics, this intensity correlation has been used now in quantum physics, lab quantum physics, or it's our bread and butter every day. So if you have single particles like atoms, photons, ions, the one way how to prove that it's single particles is a kind of a Hanbury Brown and Twiss or Ongo-Mandel correlation technique. So we always do intent or clicks correlation experiments to prove that we have single particles. So this nowadays is, of course, the the heart of all what we could now call quantum technologies. And so this is really something which has been developed, and the fact that this has such an impact on quantum technologies pushed the whole instrumentation and technology very far. And now we use this push of technology to bring it back to astrophysics. Also, okay, so there's another way. So you can not only prove that you have single particles, you can also prove that you have non-classical correlations between particles, so entanglement. This has been shown, okay, by Clauser first and by Alain Spey, and that's in with three particles. And this is now, of course, at the basis of quantum cryptography, and maybe one day in quantum computers we forget them. So at least what I want to say is everything depends on intensity correlation or clicks. You make clicks and you look at how they arrive together, what polarization state. So everything is based on correlations. And all this development has been possible by the foundations by Hanbury Brown and Twiss and Glauber, which was done in the 60s. And then the technology came up later. Okay, so why do we think today there is an argument to bring this back to astrophysics? So first, so the interferometric Antoine Labeyrie type of VLTI type of interferometric combination requires to make fringes which have to be stable at the wavelength precision, so micron precision, which if you have baseline of 100 meters is very difficult to do this. Also, it's very sensitive to atmospheric turbulence, so you need adaptive optics techniques. So it's a very fragile way not to destroy the fringes. And also, if you have a very large baseline, because the stars move in the sky, the Earth rotates, and then the apparent motion of the star in the sky move, and then there's an optical delay between photons arriving on one telescope and the other telescope. So you have to compensate for this. And if you have hundreds of meters distance between telescopes, you need to have delay lines which move over hundreds of meters, which they do at the VLTI site, which is really impressive, but it's very difficult, and so far no one has really option to extend this to longer baselines like kilometers or more, because you would need to have rays moving with micrometer precision over kilometers. There's no reasonable project now to do this on Earth. And so intensity correlation have a big advantage compared to this. They are insensitive to the precise micrometer precision positioning of the telescopes or the distances. And the same way, they're not very sensitive to atmospheric turbulence, so you don't need micrometer precision. Millimeter precision is good enough, so you mean the factor of 1,000, which is important. You don't need to have a very good telescope, so if you have light buckets, that's good enough as well. And it can also work at very short wavelengths, which is more difficult if you need a stability at the sub-micron precision in interferometric imaging, but here it's very easy. And so one thing we also exploit is that we don't need to build new infrastructure. We can use telescopes which exist and we look where they are, and then we take the light in these telescopes and we just look at when the photons arrive and do data reduction with the instrumentation which exists. Again, the price to pay for this advantage is a very bad signal-to-noise ratio, which means longer integration time. Instead of milliseconds, it's hours. So that's this is the bad thing. We have to find a solution to this. And so there have already been, so this is known for a long time. There have been strong advocates to revive this intensity correlation technique, in particular in the Cherenkov telescope array community, because they have large collectors at large baselines, and they wanted to make best use of the instrumentation for other applications. And so David Dravins is one of the main advocates for over the last 30 years to say we should come back to intensity correlation and use the infrastructure we have in CTA to do this type of intensity correlation. Okay, so this was a long time ago, even before 2008, he already started doing this type of advocacy for this. There have been early attempts to revive this in Italy, also in Chile, not really successful because it was not easy. The detectors in these days were not good enough. There was a recent experiment in Singapore by taking sunlight, but making a super narrow spectral filtering, but it works. But all this was on a single telescope, so no imaging at this point. And so this is where we came in. Somehow naively, we didn't know all the problems, but I came from background for quantum optics, and I thought I want to go for quantum optics in space. And so that's why I engaged in this without all the trouble which other people had so far. So the idea is that you try to first make laboratory experiments. This is important to convince the people who run the telescope that you do serious physics. Because if you have ideas from the 60s to say, yeah, that's didn't work, we know. So we have to prove with numbers that we can do things. So so if you have intensity correlation, if you have a spectral filtering, this allows you to control the coherence time. By the narrower the filter, the longer the coherence time. So with an optical filter of 1 nanometer, we get coherence time of picoseconds, which is still much shorter than the time resolution we have with our detectors, which is of the order of hundreds of picoseconds. This means that instead of having a bunching of 2, you have a convolution and the bunching goes down to less than 1%. But okay, you can, and this is why you need to integrate long time to get a single noise ratio, which allows you to see a bunching of less than 1%. If the bunching would be 2, it would be much easier. So this is why we need to integrate long time. So we showed that this can be done in the lab. And with this, we were able to convince our colleagues here in Calais that we can attempt this at their telescopes. So this is setup which developed, which was a very compact setup. You will see it in the next slides. This holds in my hand. So the light from telescope will be focused on the multimode fiber, then split into 2, and we make intensity correlations here. We have a guiding camera, some filters here to increase the coherence time, and here's some numbers if someone wants to look at the numbers for the older experiment. So this was developed in like 10 years ago almost now. And so then we went to Calais in 2017, and first we tested this at a single telescope. So here you see Guillaume Labéry, which is actually the son of Antoine Labéry. And this is our instrument. So you see it holds in the hand, and it's connected directly to the output of the telescope here. And this William Guérin standing in front of the dome. And here are some typical numbers for a 1 meter telescope. This is a small telescope, nothing really special, but it's nice to have it easily accessible for us. And so that was in early 2017. And we registered with this technique intensity correlation on 3 bright stars, which I mentioned here. So you see the intensity correlation with a bunching, which is exactly what we expected from the lab experiment. So everything works as expected. Most importantly, for this data here, we show that the signal to noise ratio decreases as expected from the formula. So this means we have no spurious correlation. We're limited by shot noise limitation, which means that we were really at the fundamental limit of photon detection. So these are the early experiments where you have single photon clicks and not a continuous measurement to do intensity correlation. Okay, so this works. That was February 2017. In fall, we went back again now with 2 instruments, and we used the 2 telescopes at the same location, and we looked at the correlation between the 2 telescopes. And this means we can make imaging, we can put the number on the angular diameter of different stars. And this was actually the first time it has been done since Hanbury Brown and Twiss in the 60s. And now with the modern quantum optics, single photon detectors we have available. So this is a kind of a I think this marks the revival of this technique for imaging using intensity correlation with quantum technology. So this is the twist we want to add to it now. But so this works 2017. Then in 2018, we measured even emission lines. So you can change the filter and you can show that you get even more bunching than what you expect because the emission line is narrower than the filter you can put. So everything works. And in 2019, we were allowed to go to a 4-meter telescope in Chile at SOAR, because we have some connection with Brazilian colleagues. And so even though it was a very bad night, we only have a few hours observation time, we were able to see some bunching on eta car on the H alpha line. So we could, what is important here is we could show that we can go to a big facility during daytime. We plug in our instrument here, which is shown here. We take data during night. Next morning, we spoof this off again, and they can work again as before because they don't want you to mess up with their instrument. So this was important to show that we don't mess up with big instruments and we can take data. So this was in 2019. Then in 2022, we were allowed, also we were able to go to the VLT site, so that's the UTs and the ATs. So we were able in 2022 to measure intensity correlation on 2 AT stations. And this worked well. And then in 2023, we went back and we make measurement with 3 AT stations. So this showed that we can go to the big facilities, use the instrumentation which exists, and then make our intensity correlation. So this is something which we did in the last years. And now the question is, what can we do more than this? So we showed that this technique is possible. And now we are not alone. So somehow, independently of our goal, which was initially quantum optics, there were other groups, many of those coming from the CTA community, so Veritas, Magic, the big telescopes in US, on Canary Islands, and they now have also in the last few years measured very nicely with a much better signal noise ratio than we did actually, because they are larger collectors, intensity correlation on many different stars now. So this is a technique which is now developing. There are different ways how to do it. One is with photon buckets, so CTA, which doesn't have a very good optical quality, but they have a large collecting area and good baselines, or optical quality telescopes as we do in Calern or at the VLT site or in Paranal or now in Hawaii. So there are different ways, and the constraints are a little bit different. The filtering and different things you can do don't have the same limitation. And of course, I'm very objective. I think our approach is the best. Who knows? We'll see in future. So there are different communities who push this intensity correlation forward to see who can do new science with this technique. And so there are now the same has been done at TAS in Namibia. There's a group in Germany, in Erlangen, the second one, which is doing this as well, and a group in Switzerland. So there are many groups now, there are 5-6 groups, and it's a growing community who is joining this instrumentation site. Now, so it's a growing community. There are workshops. There's been one in Ohio 2023. Last year, there were 2 workshops. One we organized in Porquerolles here close to Nice, another one at the Pyramid Institute. This year, there will be one in Germany close to Erlangen. So there's now a community which is trying to meet once a year to discuss the development of instrumentation and, most importantly, find science applications, what to do with all this instrumentation. So far, I basically showed you the instrumentation side. So why do we do all this? And this is where we have this new project, which I call Intensity Correlation for Stars, which got funded by the ERC. And it has, again, it's a double aspect, high angular resolution and quantum optics, which is, again, you will have understood that that's what I like most. The idea is, again, so to combine the light from 2 telescopes, make intensity correlation, as I showed you before. And compared to other ways how to do this, the imaging, because of the wavelength, so we can go up to 400 nanometers now, and we can have baselines of kilometers. This gives us the same angular resolution as the Event Horizon telescope, which was done in the millimeter range, and they had the whole Earth as a baseline. So the goal of this community is to get images of accretion disks, maybe even rotating disk, and then look at more fundamental science, what happens in black holes. So this is a big motivation, and so one has to show that this can be done. So what we need to do now in the next few years is to show that we get a good signal-to-noise ratio, which can overcome this limitation which Hanbury Brown and Twiss had, and that's why he stopped. But the resolution will be fantastic. If this can work, we get a fantastic resolution. Okay, so up. And so this is the main part where you have to work hard. So this is the formula for signal-to-noise ratio when you want to look at the correlation function for distant telescopes. So there's a kind of a formula. The first thing you will see in this formula is that it does not depend on the filter which I will add to make increase the coherence time. And the reason for this is that if I make a filter narrower and narrower in some regime, I have less photons, so that's bad for the signal-to-noise ratio, but the bunching goes up, and this exactly compensates. So in this regime of parameters, the signal-to-noise ratio is independent of the width of the filter I will put. This allows me to take a dispersion and work at put many filters, and behind every filter I make an intensity correlation experiment. So I do multiplexing. So I can do many channels at the same time. And this gives me an increase in signal-to-noise ratio, which is the square root of the number of channels. So what we apply now for our experiment is we have 16 channels. So this gives an increase in signal-to-noise ratio of factor 4. Then instead of having the 1 meter telescopes in Calern, we go to Hawaii, where we have initial improvement from KEC, which is 10 meter, and CFH, which is 4 meter. And so this is much larger area than what we have so far. And this gives you an increase in single noise ratio of factor 40. That's important. And this is proportional to the area of the disk, so the square of the diameter. So this is a big telescopes help a lot here. And then it depends on the function you want to measure, and it goes like square root of observation time. That's why you need to pay to integrate long time, and divided by the timing resolution of the electronics you have. In the past, we had electronics of 100, 200 picosecond, and now with fast detectors, we can reduce this to few tenths of picosecond. So we win again, we win a factor of 16 or in the timing resolution, and maybe factor 4 in single noise ratio. So if you put all this together, we hope to win a factor of 600 in single noise ratio, which translated into observation time is a factor of 400,000. And this is impressive. So if you tell people from the observatories that you can do the same data, but 400,000 times less observation time, this is a big impact. Basically meaning that what you could do, what we now be able to do in one night, it would just have been impossible before. But we need to prove that we can win all these factors. That's why we have to work in the lab and on testing stations before we can go to Hawaii. And so with this, we bought a lot of detectors. So all this is now technology. I know if this community now is where we need to discuss this, but this is really at the heart of the progress. We need to get control of better detectors, many pixels, and no spurious noise, no correlation, which are not with the one we wanted. So this is really at the heart of why we think we can improve this signal noise ratio. And then, of course, also, if we have a good signal noise ratio on the two stations with the timing of few tenths of picosecond, we need to know where these telescopes are, and we need to synchronize our detectors. So there's a solution with White Rabbit, which is off the shelf, commercial. That's what we buy. And we try to push it with our colleagues at the Lunar Ranging Station to picoseconds in the future to be one step ahead of the technology for the next 10 years. And also one thing which is a little bit surprising, even though we don't need to have a precision of millimeters for our micrometers precision of the telescope, millimeter precision is good to know where the telescopes are. And most of the telescopes, they don't know where they're located with this precision. So we need even to do a geodesy project to know where the telescopes are. It sounds strange, but it's not such easy because you need to know where the light is focused, and sometimes you have two axes which don't cross. So it's not an easy problem to define, but this is by itself a project which we have to solve. Okay, and if all this works, this is the project which was funded by ERC. So if this works, we are going to aim at Sirius B, which is the companion of Sirius A, which is a white dwarf. So it's a quantum degenerate family gas of electrons. So it's a quantum object. And we want to use intensity correlation, so quantum tool, to resolve angularly this Sirius B, this white dwarf. And using the telescopes Keck and CFH, and with the numbers I just gave you, we should be able to have a signal noise ratio of 6 in 1 hour observation time, which would allow us, for instance, to say that the relativistic corrections you have to add to make a prediction of the size of Sirius B are important or not. So this is something we should be able to say yes or no, you need relativistic corrections. And maybe you can even test more. So there's no big reason to think that these models are wrong. I think everything is fine. But as a physicist, I think every time you can measure and validate the model, you have to do it. Because if you don't test the models, you will never find the surprise. So you have to test it. And we're going to test if the model for the size of Sirius B is what is correct and what really nature is telling us. So this is a big project. This is something which is impossible to resolve with any instrument we have so far on Earth. So this will be the best microscope for stars, which is possible. But it's a hard work because you need to do all this multiplexing, timing, synchronization, geodesy. Sirius A is very close by, so you are blinded by big stars. So it's a challenging engineering problem, but it's well posed and numbers seem to be okay. So we have to work, but it should be okay. Okay, so and once this works, so we already have, of course, looked at. So if this works, we have no doubt that it will work in 4 years from now, let's say. What can we do beyond this? And then we can go for Wolf-Rayet stars with so sub-milli arc-second resolution. We can look at binary white dwarfs, at black hole accretion disks. So all these type of targets should become accessible if we can prove that we can do this multiplexing and this scaling up with this noise ratio, which I showed you previously. If this works, then all this should become accessible in the next 10 years. And then you can dream of, okay, what type of fundamental physics test you want to probe with these imaging techniques. And this is maybe something people of this community can participate to shape the goals, the science goals of what we can do with this instrumentation. Okay, so then now quantum optics, of course, deep to my heart. And there's a big bonus. Sometimes you only need a single telescope to do this. So it's easier to do on sky than having access to two big telescopes. So it's a little bit easier technology, but the science is a little bit more complicated. So a first example to show why this is challenging, basically, we have no idea what we'll see. There are a lot of open questions. And so I really would be happy if anyone who is listening to me, and I try to reach out to other people, participate in the science case and in the theory and the modeling of what we can expect. This is an example. So in cold atom community, there have been experiments done by in degenerate Fermi gases by Wolfgang Kettle, MIT, John G. and Gilla, and a group in New Zealand, showing that if you have a degenerate Fermi gas, light scattering inside is forbidden because you need to, if you want to scatter light by a fermion, it has to recoil, and if this state is occupied, this is not allowed. And so this is called Pauli blocking. And so experiments have been done with a temperature which of the order of 0.1 times the Fermi temperature. That's what people can do in the lab. It's very difficult to get much lower. But in the white dwarf, we had 10 to the 6. It's very, very, very down in the degenerate regime. So obviously, there will be no light scattering inside the white dwarf, but we still see light from the white dwarf because at the boundary of the white dwarf, the density goes down. And there, the Pauli blocking will not be effective. Now, the question is, the light we see from the white dwarf, from what depth of layer does it come? And does are there first corrections due to an onset of Pauli blocking, which would modify intensity correlation? So this is the type of questions I discussed with experts in Gilla who do the experiment. This is an open question. So we don't know how Pauli blocking, when it sets in, will affect intensity correlation. So this is a question we would like to see. Maybe we see corrections of Pauli blocking on Sirius B when we measure it, even on single telescope. No idea. So anyone want to join, I would be very happy to collaborate with you. Another thing which has been put forward by Glauber is that if you want to make the difference between laser light and thermal light, which is collimated and filtered with a filter, you cannot make the difference if you just look at the optical spectrum, which corresponds to the G1 function, the field correlation function. But if you measure the second order covariance function, so G2, then you very well can make the difference between a thermal light and a Glauber state or coherent state, so laser light, so light based on stimulated emission. And so, okay, so this is a very clear case where intensity correlation can do things which amplitude in correlation cannot do. And so this is one thing we want to exploit. And so there's something called random lasing. So random lasing is, oops, this is some strange thing. So first, how is laser working? Laser, you have mirrors here. You have a gain medium, you pump it, and then photons will be spontaneously emitted, and some will be recycled by this cavity and go through this gain medium many, many times. And then there's stimulated emission processes here, and the cavity will amplify this stimulated process here and also direct light out. So there's a gain medium, there's a cavity, and this gives you the laser above the threshold if you have a sufficient amount of recycling, or the finesse of the cavity is good enough compared to the losses you would have in other directions. Okay, so that's a regular laser. Now, Letokov in the 60s proposed a different way how to do this lasing by getting rid of the mirrors. And so you have to put energy in it. So you do pumping, you have to insert the energy. And then instead of having mirrors to recycle the photons many times, you have multiple scattering. So the photons stay inside many times and they're amplified all the way they do random walk inside, they're amplified. And the loss compared, which would be the mirrors here, is when they come to the surface and they emit. So the loss is proportional to the surface, and the gain is proportional to the volume. So it's like an atomic bomb. It's also called photonic bomb. So there's a critical threshold for random lasing. And this is what might be possible in astrophysical settings. You might have pumping, optical pumping, you have multiple scattering combined. And Letokov, at the end of his career, really was looking to details about astrophysical lasing, and he identified particular Eta Carinae as a very likely object to be a location of random lasing in astrophysics. But to prove that it's random lasing, you need to measure intensity correlations. So this is what we want to do. So the pumping scheme for Eta K is that the central star here, so there's a lot of iron dust iron atoms ionized around the central companion here. They are pumped by the Lyman alpha light of hydrogen of the central star, and there are some decay channels here, and some are long-lived metastable state where you can induce an intensity population inversion between two states, and this is where the stimulated emission will occur. And there are a couple of lines which have been identified as candidates for population inversion and stimulated emission, and that random lasing if you have sufficient amount of scattering. So this is what we want to see. We want to see if we can check the stimulated emission process and random lasing on eta K with the telescope and see if there's a modification of this intensity correlation from bunching, which you expect from thermal light, to like a coherent laser light emission. So that's what I sold to the ESC panel, and they bought this. So they funded this proposal. Actually, the story is a little bit more complicated because this black and white thermal light, laser light, it's just a very extreme model. In practice, it's much more complicated. So there's there are deviations, there are possible deviations between the intensity and field correlation functions. If you have non-Gaussian correlations, there are a couple of experiments which have looked at intensity correlation in random lasing setups, including one where I participated, and we saw a very different behavior from V2 going from thermal below threshold to laser above threshold. There was a mode locking scheme, so it's not clear at all how the intensity correlation will behave when we cross the threshold. And also, we don't know at all what the eta Carinae, for instance, where it sits compared to a possible threshold of random lasing in astrophysics. So all this is still very open and needs to be studied. And so we're going to do this in lab experiment first to understand how intensity correlation will be modified when you cross a random lasing threshold. So all this is still open for research. Another thing which is interesting is that if you look at photon statistics from a source, so the number of photons per optical mode is given by this Planck's law here. And typically, stars are a few thousand Kelvin hot, and the energy of a photon is much larger, so you can develop this exponential function here. But for very hot star and low energy photons, so in the infrared, you might have more than one photon per optical mode. And this had already been identified by Mandel and Wolf many years ago. And so the question is, does this modify G2? And so I'm discussing now with different people how to look for hot stars and measure the intensity correlation on single telescope from hot stars. And actually, I don't yet have anyone who gave me a prediction how the intensity correlation should be modified when we go for hot stars compared to a few thousand Kelvin star. So this is an open question. I discussed with some colleagues, and they say, yeah, sure, probably it should be modified, but we need to make a serious theory work and predict how it should scale when you change this parameter here, h nu over kt, and if you do intensity correlation from starlight. So all this is still also open up for theory, and experiments might come very soon. This year or next year, experiments might come. So it's something where progress might be very, very fast, much faster than the angular imaging of Sirius B. Another thing, last thing, and that's actually where we discussed with Dennis initially, is that so there have been attempts on looking at what is the fundamental limit for collapse models for wave functions. So that's a kind of a very fundamental topic. There are many models, and I'm not an expert on this at all, but I've read that people mention different type of features where entanglement would break down, and this can come from different type of features. There have been experiments done by a Chinese group led by Pan on Misius on the satellite, where they shared entangled photons, and they basically saw no modification. Everything behaves as if there would be no decoherence mechanism, but they put an upper bound on potential decoherence mechanisms. And this upper bound depends on the distance you can use your telescope. It's like an interferometer, and you want to see the larger the distance, the more precise and the better you can put bounds on this model. And so far this has been done with low orbit satellites, 400,000 kilometers, something like this. And here's a picture which I took from this reference here, is that maybe we can dream of going further away than just in satellites. going for planets or for different stars. So if you find, for instance, a coherent light source from a star which is a few parseconds away, this just blows up the scales. And if you can put any bounds on fundamental decoherence mechanism, this will be difficult to beat with Earth-based experiments. So that's one of the dreams which we want to look at, but we need to do models, realistic models, putting numbers on this. And I'm an expert. Well, my team is expert on instrumentation, but we have no idea how to put numbers on this. And so this is where we need to have expertise from different communities. One thing which I discussed more recently is using a satellite which is already flying, Psyche. This satellite is has as a mission to study Mars, okay? But at NASA, they decided to add on board on this satellite a laser, and this laser is being used for deep space optical communication, basically to improve the bandwidth of the data rate of information we can share once we go to Mars, or if you have a mission on Mars to transmit data at a faster rate. And so this works. So Matt Shaw, which I mentioned initially, he's lead of this DSOC mission here, part of this Psyche mission. And so this works, and the laser now is at close at the distance of Mars, so at 3 AU units. So it's a laser which is furthest away from Earth we have so far, and there's no hope to get another system with laser that far away in the next 10 or 20 years. If you decide to do it now, the mission will fly maybe in 10 or 15 years. So this laser exists. And so what they have done is they transmitted pet videos. So it works. So this is a video data stream from 3 AU units apart. So that's okay. It works. A good database. But so when I saw this, I went to Pasadena and discussed with them and said, maybe we can do a little bit more than just transmitting videos, which is important for what their mission. But I want to do other type of physics. And so the idea is to do the following: take the laser on board of Psyche and look at intensity correlations. And so the idea is that suppose there's so the light coming from this laser here will come to the telescopes. This should be Mount Palomar. That's Table Mountain. They have two sides. Come back to this later. And so if this is a laser, so that should be coherent. So G2 should be flat. But if there's anything on the way between the source and the detector, which makes the wave function fluctuating, then you will see this fluctuating field arriving at the detector. So this G2 function might be modified by background of fluctuating ingredients, whatever it is. And so this could be in gravitational wave background. And it would be even better if you can do this with two different telescopes, because if you go for a single telescope, there's kind of a common mode. All this light, we see the same fluctuation. But if you have a big baseline here and they have a baseline of 130 kilometers and they already have seen photons on the two stations here, but they did not yet make cross correlations. But that's what we discuss right now. So the question is, can you put numbers on how sensitive this type of detectors would be for gravitational waves? And this is something I'm discussing. I tried to convince Serge Reynaud, who has been involved in other type of gravitational equivalence principle measurements in satellites. So he knows all these effects very well. And so the question is, can you put numbers on this? Now we have a huge distance here, the best we have so far, as long as we don't get current light source from stars. And we should be able to exploit this. And so this is just an example of the G2 measurement they just did recently on Mount Palomar. So, but it needs to be normalized. So it's going on right now. The main trouble here is that DSOC mission is expected to be finished end of August this year, because it works. So basically they say it works. Thank you. It works. We know how it works. And now we have to find good science cases to convince NASA to continue sending light from this laser to Earth, that we can do something else with it. The laser is there, the energy is there, but so we just need to convince the people that don't dismount the detectors, that every now and then this satellite Psyche, which should do something else, looking at Mars or something else, every now and then we'll point at Earth and send stream of photons, and we will do science with it. So it would be nice, even in this community here, and discuss this with the people at JPL, they are trying to gather support from the community to get a good strong argument to continue this type of instrument, because else it will be discontinued, and then we have to wait for many years before we can get again this type of system up to test fundamental physics. So I like this type of physics. I would be happy if this could be put numbers on it if it's reasonable or not. If you find that this is 100 orders of magnitude away from everything reasonable, then we should stop. But if it's close to become reasonable, then we should do the experiment. And with this, yeah, so this is what we dreamed of. So for the ultra high angular resolution, going for accretion disks, and this can be done if you combine light from the VLT side, the ELT side. So we don't need to build new instruments. So all this should be feasible. It's mainly engineering, hard engineering, but should be feasible. And the quantum optics, it's a speculation part. Can we detect gravitational background wave detection, Pauli blocking in Fermi gases? If there's simulated emission in any source, the forces will be modified as well. Usually radiation pressure forces, you have photons going from one to a particle to another, it pushes the particles away. If you have stimulated emission, if one photon goes here, it will emit two photons and the two particles can attract it. So you can have attractive forces if you have stimulated emission. But first we need to see that you have stimulated emission before we can dream of applying long range 1/r attractive forces corrections due to stimulated emission. That would of course be fantastic as well. But so we need to find a signature that there's stimulated emission at play somewhere in astrophysics community. And with this, I thank you for your attention. And of course, if there are questions by email now, whatever, I'm happy to take everything. Thank you.
Yeah, thank you very much for that inspiring talk. Great ideas and things that you are doing. So is there anyone with a question from the audience? Yeah, just Stefanov, if you Andrei Stefanov.
Okay, yeah. I can start. So thank you for the talk. My question is about this high angular resolution imaging. So if I understood, on the one side you want to have single photon camera on each telescope, but then you show two telescopes with some few hundred meters. So usually in this kind of trunk of telescope array, so the resolution, angular resolution is given by an array of telescopes that are separated. So you have many telescopes, and so in the Fourier space you have many points. So how is it with only two telescopes and cameras?
Yeah, no, so if you have only two telescopes, you basically only measure one Fourier component, okay? Which is, you get the diameter, but you don't get an image. And then actually because of the rotation of the star, so the U in this Fourier space, the telescopes, they make some angle, they curve. And so you get a little bit more Fourier components if you integrate at different times during the night. But of course, this is why the CTA array is much better, because they have a large number of components in the Fourier space. Yes, and so the question is, how can you do image reconstruction with a minimum amount of components in the Fourier space? And this is, there's something called closure phase. So if you have got three telescopes, you can do even much better than just a pairwise combination. And so people are working on this, but there's no, we don't have an easy solution. It's just angular resolution. You can, for instance, measure the size of something. That should be possible. But if you want to measure the more complex image, like Betelgeuse, and get all the speckled grains on or all the grains on Betelgeuse, then you need more detectors. I agree. That's a limitation. Yes.
Okay, and if I may just to ask again, and what is the advantage of having the single photon camera then instead of just a single pixel detector?
Yeah, no, but a single photon. So the resolution in the Fourier space comes from the distance between the telescopes. And now at every telescope, if you take a camera or a detector, so either you put all the light on the single detector or you put it on the camera, it does make a big change, because the different Fourier components which arrive on the single telescope are very close by. So it's not.
But my point is, but the price to use those cameras is that they have lower efficiency. They are worse than just a single pixel detector. So why do you want to use the camera? So still.
No. So actually, we don't use cameras. We will use single photon detectors in the optical quality. But at CTA, so the idea is to exploit at best the instruments which exist. So if they can exploit cameras which exist, they don't need to mount new things. So it's kind of optimization and not a fundamental. So there's a compromise between what's the ideal situation and what is the best cost efficient compromise.
Thanks.
All right, Lorenzo, do you want to ask a question?
Yes, thanks. Very interesting. Thank you. I wanted to ask about the signal-to-noise ratio formula you showed, the one with the square roots. Typically, those square roots come from the central limit theorem, right?
Yeah.
So,
Yes.
okay. So where can I find that?
The formula or
paper that
oh yeah, the references. Okay, I can yeah, so this has been so we have oh okay. So maybe send me an email, I will send you the reference. Yeah. So this has been
great,
derived
thanks.
by
Yeah, my
ways.
question is typically those square roots come from central limit theorem, and maybe some quantum effects like entanglement that typically helps, right?
Oh, sure. So this is why if you go for the hot stars, which I mentioned here, things might change.
Okay.
Things might change. You have many more. Yeah, all this. Yeah, so this would be interesting. So if someone wants to look into the details, to go back to the basics of how these formulas have been derived, that would be interesting. There might be new things coming up.
That's exactly why I was asking.
Oh yeah, no, that would be so far. No one in the community I meet is questioning this. Oh, we take this formula, but I fully agree. Someone has to go back to the basic and see with the new parameters where we run experiments on the quantum regime if this has to be revised.
Yeah.
Okay, that would be. Oh, if you find a adapted formula with quantum correction to this or whatever, wow, that would be fantastic.
Great. Yeah, sure.
Oh, that would be fantastic. Yes.
Okay. Good.
Yes.
Thank you very much. By the way, very nice talk again.
Oh, thank you.
Thanks.
Albert, do you want to?
Yeah. So yeah, again, very interesting talk with a very broad range of interesting topics that you presented. So I had, I guess a question about one of the last things that you were mentioning in connection with this possible gravitational wave effects on these measurements from this deep space optical communication NASA mission. So I'm not sure how much you said that you are a little bit working on that with some collaborators, but how much you've thought about it. I mean, the first thing that comes to mind without really having thought carefully about it is that, so in principle, it would seem naively to me that if you send a coherent state, even though you have a gravitational wave, let's say, passing through, it will remain a coherent state. So the mode will be modified. I do see that, of course, it will be modified in a time-dependent manner. So I'm not sure whether that's the effect that, in fact, you would be after.
Okay, here's just a picture. But what people do, for instance, to produce quasi-thermal light is they take a laser beam and put it on a ground plate, glass plate, which is rotating.
Yes.
So this gravitational is like it's a phase fluctuating intermediate medium between the source and detector. So the medium, the space between the laser and our detectors, it's like a random phase object, time-evolving phase.
Yeah, okay. So I guess that then we get into a little bit the discussion of you're looking more at some sort of stochastic background of gravitational wave rather than a coherent.
Yes. Stochastic background. Yes, sure. Yeah. It's not. We don't look. It's a background. It's not like an event of merging black holes. No.
Exactly. So not or spiraling. You're looking at the stochastic background. So
exactly. Yes.
That Serge has worked on. But then I guess it has to do a lot with this stochastic background. What are the sort of characteristic correlation times and so on? Because I guess in your case the times are rather short that you have access to, right? With these. This G2 that you're measuring, the tau there, I'm not sure what's the range of values, but presumably.
Yes. Yeah. So so the thing is, this is why so that's what I'm discussing right now with Serge. So that's why I think on the single telescope it's probably difficult, but on different telescopes there might be different incoherent background coming to the two. So I don't know the time scales and the amplitude of these effects, and this is where we need to put numbers on it. And then we'll see. So one thing which is easy for us to do is take a long integration time, but the coherence time itself is short. So if there would be a decoherence over minutes, this will be lost in our background, because except if the amplitude is very large.
Right. Exactly. So
just to show you an example, something which surprised us initially. So I know if you can see this here. This is intensity correlation function, which we measured in one of our setups. Okay, so it's G2, whatever. So we measured initially, it's not shown in this plot, we wanted to measure G2 at the sub-nanosecond resolution and we wanted to see if the bunching is modified compared to same as we did in the astrophysics setting. And then we were just looking at the central part here, and it was more or less flat. But I saw a curvature, and then what I saw is that at a much longer time scale, you see microseconds or milliseconds, you have a structure.
Mm-hmm.
And this is easy to get for us. So if there's a structure at longer times, it's easy for us to get. So this was, you see here, there's a modulation of the detected light at almost millisecond timescales, millisecond timescales. Even though detectors are precise in picoseconds, we can measure time evolution of the order of microseconds or milliseconds.
Well, I guess then that's a little bit then the follow-up question related to this point, which is what's the longest times? I mean, in this particular example that we were discussing, are you limited by the sort of, I don't know, some sort of coherence of the laser source that they use in the...
Yeah, no, so in practice, in practice, it depends on the type of lasers they have on board of the satellites.
Mm-hmm.
And so from what I have from discussions, is what they use it is to send cat videos, okay? And so how do they cat videos? They do short, long pulses, few nanoseconds, long, short, long, short. That's how they transmit information.
Okay. So
and their laser cannot be easily operated in continuous regime. So
Mm-hmm.
we're probably limited by the longest pulse duration they can do on the laser.
I see.
And this is a few, we're still discussing. So the issue is that they are not allowed to share all data with the public because it's export limited information on this mission. So I'm not allowed to get all information. But so far from what I know is that what they have used so far is up to like 8 nanoseconds duration. So which is very short. If it would be continuous laser, you could go for minutes. But I don't think.
But then, if I understand correctly, what you were explaining earlier, that could potentially give you some information on a stochastic gravitational wave background, but with correlation times of the order of gigahertz, not for the frequency of the gravitational waves themselves. But actually the stochasticity. So it's exactly higher frequency gravitational waves than would have in this background.
Okay. Yeah. So it's clear that I have no expertise at all. That's why I need people who know what is a reasonable model of gravitational background
frequencies and so on.
Mm-hmm. Frequencies, amplitudes, all this. Yes, wavelengths. Many things. And this I don't know, and that's why I'm discussing. I try to convince experts to see to invest their time on putting numbers on it.
Mm-hmm, mm-hmm.
But what is sure is this is laser furthest away from Earth we have so far. So it's something. Of course, there are other things. There's also it's not only gravitational background. There's also electromagnetic interactions with solar winds. So we need to be made to make these at different frequencies. There's a lot of benchmarking. There's atmosphere, there are a lot of things which can come at the more mundane level before we go to the. But okay, just the first thing is what is the expected number on gravitational background? If it's just far away, okay, then okay.
Yeah, I mean, of course, the atmosphere, I mean, typically for these long distances, I mean, they have to use these adaptive optics and so on. So I guess that would be on top of the...
Yeah, so they're different. Yeah, so all this can be benchmarked and subtracted at some point. But so the question at this point is there any hope to see the gravitational wave background? And if yes, we have to do the benchmarking and all the, we have to, there's a lot of work to be done on this. But and I don't have the answer today. So that's what I would be happy to have experts working on seeing what can be done with this. If this was just, to dream, if we see a contribution of the gravitational background, this would be a limit to quantum entanglement, okay? Because there's a wave, a background. So how big a quantum computer can we build? This will be a fundamental limit because we'll not change our universe. That's what we have. Okay, you can shield whatever. This you cannot shield. So if there's a background fluctuation here, this might be a fundamental limit on how well entanglement we can control on Earth.
Well, actually, this is then this would be a discussion then for a full separate discussion. But it's a bit related also to some of the work by Serge Reynaud that I'm not sure how that a complete fundamental limit is, in the sense that it's a little bit related to these subtleties in the relation between decoherence and dephasing. And the point, I think that there's some of these cases that they studied sometimes for some, also matter wave interferometry and so on, are closer to the phasing, and in the sense that if it's actually a given gravitational wave with some, non-trivial time dependence, because the frequency is not a perfectly monochromatic and so on, and so you can resolve. But if it's an actual realization that you have, so in principle, you could imagine that you have some other good gravitational wave detector for that, and then it pause correct. You just correct.
Yeah, okay, no, I agree.
It's not a fundamental killer of your.
I agree. I take this argument. I agree. Yes. If you can make a compensation, you measure the fluctuation and you compensate for it. Yeah, I agree. It's getting harder to do it, but yeah, I agree.
But it's, of course, it would be something important to keep in mind for for quantum communication at
if you I don't think any quantum computer will be like this, but if you dream about the quantum internet with intercontinental distances, who knows?
That one will need to take into account eventually at some point. Yes, I would agree.
But okay, this is far away. It's dreaming. But okay, we do research. We are there to do ask fundamental questions.
Yeah. Thank you.
So you didn't talk about polarization at all. Does that play any role in your?
So it plays a role because if you have two polarization modes, these modes do not correlate.
Right.
So you can do polarization filter, then you throw away half of the photons. So the signal to noise ratio doesn't depend on this neither. So you either can you can either filter the polarization, which makes things cleaner, but it depends if you're limited by the maximum count rate of the detector or the background. So it depends in the range where you are. And in practice, so we discussed this extensively for the Hawaii question. So we could either put filters, but if you want to select polarization, you have to select the polarization from the light coming from the stars. And the different telescopes having different mounts, the polarization is modified differently. So it's easier for us not to select the polarization than to select it, but because of technical issues in the telescopes. And it doesn't change the signal to noise ratio as long as you don't saturate the detectors. But for this weak signal stars, we are not going to saturate our detectors. So we're probably not going to select to filter the polarization.
Okay, I see.
But so again, it's different. If you go for this type of effects, then of course it depends what type of entanglement you want to do. If you encode your information in time energy bins or in different polarization states, and they will be affected differently by the tensor waves, whatever. So it depends. Yeah. So you have to look at where, if you go for entanglement, you have to look in what information your entanglement is encoded in, if it's in time and phase or in polarization. This has different consequences on what type of fluctuations you get on your beam.
So thanks. And is there any further question from? Okay, Albert, please.
Well, if there are no other questions, I mean, it's actually a very short thing, but I was actually curious. I couldn't really follow in detail. You mentioned also earlier in your talk about some applications to geodesy and something like millimeter resolution. So could you maybe elaborate on that or go a bit more slowly?
So the thing is that we want to look at photon bunching at photons arriving at two different telescopes. And our timing resolution will be 10 picoseconds. Okay, so now if the star moves, the baseline will move. So we have to adapt. The timing will be drifting in continuously over the night. And if we know exactly where the telescopes are, we know exactly how this shift is moving. But and the precision of the shift depends on the c times the jitter of the electrons we have. And so if you go for 10 picosecond precision, we need millimeter precision in the position. If we don't have it, we could see, if you see the bunching peak, we could follow it, but it's easier to know a priori where the bunching is expected to be in time difference. And so for this, we want to know where the position of the focus is for every telescope. And so far, they don't care because they don't need to relate their position to the other position of the other telescope. So far, everyone is running alone. So
Mm-hmm.
we want to make these telescopes speaking together, and so far everyone is independent, and so they don't need this positioning.
Oh,
And
okay.
so
So I see that if I understand correctly, more than an application per se is more of in principle a need that you would
yeah,
need
yeah.
theoretic techniques to, as you just explained,
Yeah.
now to really get this positioning very well so that you can optimize your measurements.
Yeah, exactly. It's a positioning need. Yeah, for us, it's positioning need. But it might, okay, I don't know yet. So now we speculate. Suppose we do this even on a longer baseline between different sites. We could measure changes in the geodesy by looking at correlations. And maybe a precision which is not easy to get. So we could use the starlight as a measure of geodesy and to see at motion of whatever it is.
Mm-hmm. So I was wondering, I mean, I guess that one of the techniques that are used there, I'm not sure whether it's comparable, is with VLBAI, but I guess that BI, I mean, this very long baseline interferometry, but I guess the point here is that you can have these optical telescopes that are maybe more available and the distances could be small, and so you would have a wider set of options, I guess, then.
Yeah, so okay, we have so far we have just looked into it. Do we need to develop something for our need? And the answer is yes, probably yes. And then if we do it, we are also looking to can this be useful for someone else? But we need so far at this level, it's a need for us.
Yeah.
But it might become a feature to be used by other people.
Okay, thanks for the details on that point.
Okay, great. Yeah, so if there are no further questions, then yeah, thank you very much again. It was
Thank you.
a pleasure to have you and hear that great talk. And then see you soon. And all of you, we have another seminar in July. That's the 17th, if I see this correctly. Yes, 17th in the morning at 10. And it will be a talk by Daniele Oriti.
Before that, maybe some of us will meet at the conference in Naples. So
that's also correct.
We'll meet in person, maybe not everyone, but some.
But some of us. Okay, so looking forward to that and also to the next seminar and to meet all of you again. Bye. Have a nice day.
Okay, thank you. Bye-bye.